Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element thulium. I have a sample of it right here in my this vial right here. Hope you can see it. It's a little bit hard to see. Let's go back to the slides because I put it on my scanner so that you could see it close up. It's a shiny silvery metal when kept inside the glass vial. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to go and pick up. Check out his fantastic website, periodictable.com. Thulium is the 69th element of the periodic table. Its atomic number is 69 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Per Theodore Cleve first isolated thulium oxide, not the metallic element. He noticed that the atomic weight of his erbia, or erbium oxide, changed from sample to sample, depending on its source. From these obviously impure samples, he first isolated holmium oxide, or holmia, in 1878, and then thulium oxide, or thulia, the next year in 1879. Check out the previous episodes of Tales from the Periodic Table for the interesting path to the isolation of erbia. The American chemist Theodore William Richards was the first to purify pure metallic thulium in 1911. He started with thulium bromide and performed 15,000 recrystallizations until he arrived at something pure enough to convert to the pure metal. This allowed him to determine accurately the atomic weight of thulium metal. He was the first to determine accurately the atomic weights of many elements, and for this he was the first American chemist awarded the Nobel Prize in Chemistry in 1914. Many rare earths were obtained from an ore discovered in an obscure mine in a town called Ytterby in Sweden. This small city has 4 elements directly named after it: yttrium, terbium, erbium, and ytterbium. In addition, 2 other Ytterby rare earth elements, holmium and thulium, were named for Sweden. Holmia is the Latin name for Stockholm, and thulium was named after Thule, an ancient Greek place name associated with Scandinavia. All these elements from the Ytterby mine. Not bad for a town with a population a bit over 3,500. The Ytterby mine has many rare earths, but it isn't big enough to be commercial. One commercial source of rare earth elements is the mineral monazite. Monazite is a phosphate with lanthanum, cerium, praseodymium, and neodymium as major substituting elements, and most of the other rare earths as minor constituents. It's usually found in the form of a sand with other minerals. China, India, Madagascar, and South Africa have large deposits of monazite sands. Another source of rare earths, including thulium, is the mineral bastnasite, which is a carbonate fluoride with lanthanum, cerium, praseodymium, or yttrium as major substituting elements. Both monazite and bastnasite are mined for many rare earths. One last rare earth-containing mineral has the coolest name, xenotime. This is normally a yttrium orthophosphate, but other elements can take the place of the yttrium, including thulium. Let's take a look at the rare earth content of the previous 3 minerals. You can see from this table, thulium appears in low percentages, accounting for up to only 0.02% of bastnasite, up to 0.51% of monazite, and 0.9% of xenotime. Even though thulium oxides only occur in small amounts in bastnasite and monazite, so much of these minerals are processed for other rare earths, it turns out to be a major source of this element too. Thulium belongs to a row of elements known as rare earth metals, or lanthanides, since lanthanum is the first element in this periodic table row. Thulium is the 13th element of this series. Technically, both scandium and yttrium are also included in this group, since they're both members of the same periodic table column. Both the lanthanide row and the actinide row below it actually fit in the two spaces after barium and radium, but if we displayed the table in this fashion, it becomes too long and unwieldy to fit in books or on posters. Aside from promethium, the only radioactive lanthanide, thulium is the rarest of the rare earths, coming in as the 83rd most abundant element in the universe by mass. Actually, the second least abundant element on this chart, only 1 part per 10 billion. Not much more abundant than the Sun, it's the 70th most abundant element, twice as concentrated compared to the universe, at 2 parts per 10 billion. It's the 75th most abundant element in meteorites, about 2.9 parts per 100 million. In the crust of the Earth, it's the 63rd most common element, at 4.5 parts per 10 million. Still, twice as common as silver. Thulium is the 64th most abundant element in the oceans, virtually non-existent at 200 parts per quadrillion. And lastly, and not surprisingly, there is no thulium in us. As with most elements, the price of thulium varies widely with purity and the quantity you buy. 99% pure thulium oxide goes for about $100 per kilogram. The pure metal is about $1,500 per kilogram. It's pretty expensive stuff. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Thulium is here. I understand this looks complicated, but let's look at just thulium a little closer. The horizontal axis of this square represents time from the Big Bang to now. The vertical axis shows the proportion of thulium created by various processes. The majority of thulium present today is believed to be produced in supernovae, the yellow area. About 1/3 is produced in dying low-mass stars, the magenta area. And a small, tiny amount, that green sliver on the top, is produced in neutron star mergers. Note, the thulium produced by dying low-mass stars, the magenta area, doesn't get started until a bit later in the history of the universe. That's because low-mass stars exhaust their nuclear fuel much more slowly and last a long time before they start dying. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same. 69 protons for thulium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes and are chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 35 known isotopes of thulium, and of these 35, there is only one stable, non-radioactive isotope, thulium-169. Thulium is therefore a monoisotopic element. There are 23 of those, by the way. The stable thulium-169 isotope obviously makes up all of the naturally occurring thulium in the universe. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of thulium occupy the same place in the periodic table. Of the radioactive isotopes of thulium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest thulium half-life is thulium-171 with a half-life of 1.92 years, a mere blink in time compared to the age of the universe. So if these are not manufactured in reactors or atomic bomb blasts, you'll never see them on Earth. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1024 atoms of any isotope from the previous slide. I chose 1024 atoms because it's a power of 2 and we're going to be doing a lot of dividing by 2. If you wait one half-life, half of your isotope will decay and you'll have 512 atoms left. If you wait one more half-life, half of that half decays, leaving you with 1/4 of the original 1024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's one remaining atom after 10 half-lives. If you waited one more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Thulium has a medium density at 9.32 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter, and I've put up more densities for you here. You can see that thulium is a little denser than copper at 8.96 grams per cubic centimeter. Let's look at the densities of more elements. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're face-to-face again. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, thulium's density is 9.32 grams per cubic centimeter, the magenta circle just above copper. Thulium's melting point is 1,545 degrees Celsius, or 2,813 degrees Fahrenheit. It boils at 1,950 degrees Celsius, or 3,542 degrees Fahrenheit, only 405 degrees Celsius above its melting point. If we compare the size of the thulium atom to that of hydrogen, we'd see something like this. The thulium atom is a little over 4 times the size of hydrogen. All the lanthanides share the property of those 2 loosely held outer electrons, and this makes their atoms fairly large. By the way, a picometer is a trillionth of a meter. Atoms are very, very small. Here are atom sizes sorted from largest, cesium on the left, to smallest, helium on the right. Thulium has the 14th largest size atom of the elements. All the rare earths are fairly large. I'll mark the other lanthanides in blue. Notice how they're all clustered towards the top of the chart. As I mentioned, they all have those loosely held outer 2 electrons. Thulium is a soft element, coming in at 1.77 on Mohs scale of hardness. You could cut it with a knife, which are usually made from stainless steel, which has a hardness of around 6. You could even scratch thulium with your fingernail, which has a hardness of 2.5. Thulium does not expand much when you heat it. It has the 35th highest rate of thermal expansion, about 13.3 parts per million per degree Celsius. This means that if you had a 1 meter long bar of thulium, we're going to have to magnify this by a factor of 10 just to see it, and you heated it by 1 degree Celsius, it would get longer by only 13.3 millionths of a meter, or about 1/5 of a hair width. Here's the periodic table of the spectra. Thulium has a complicated set of emission lines with a few extra bright green emission lines. These emission lines uniquely identify the element to scientists using a technique called spectroscopy. Let's take a look at a few applications of this rare earth element. Some are a bit esoteric, but I'll do my best. We are dealing with esoteric elements in the lanthanides. Because of those bright green emission lines we just saw in the thulium spectrum, it can be included along with other elements in metal halide arc lamps. Here's a typical spectrum of metal halide arc lamps. The inclusion of thulium iodide in the arc bulb changes the light emission of the lamp, enhancing the greens, making the light whiter when seen in combination with other elements in the lamp. This application is a bit complicated to explain, but thulium has a fairly high probability of capturing slow neutrons, like the ones we find in a nuclear reactor. This prevents those neutrons from participating further in the fission process. Most of the rare earths, except for cerium at the bottom there, fall near the top of the chart, and a few lanthanides are even better at absorbing neutrons, but thulium is still pretty good. If you're building a nuclear reactor, you want tight control over the fission process going on inside the reactor core. Fission of the uranium atom happens when it's hit by a stray neutron. The extra neutron destabilizes the nucleus, which then splits into two smaller, lighter nuclei. The split, or fission, of the atom also releases several additional neutrons that are now free to cause more uranium atoms to fission. Since many neutrons are released by a single fissioning atom, and each neutron can cause a further uranium atom to fission, the reaction can grow exponentially, resulting in an uncontrolled release of energy. If you were developing a nuclear weapon, this is exactly what you want. In a nuclear reactor, however, it's the last thing you want. To control the fission reaction, you need to absorb a critical number of neutrons. Some elements, like cadmium and thulium, are very good neutron absorbers. In a nuclear reactor core, control rods of these absorbing elements, or their oxides, are interspersed among the uranium fuel rods. Pulling the control rods out of the core allows more neutron reactions to take place, heating up the core. Pushing the rods in slows the reaction, cooling the reactor. Speaking of radioactive isotopes of thulium, one in particular, Thulium-170, with a half-life of 128 days, may have a couple interesting applications. As you can see from this 1954 New York Times article, a small X-ray unit was developed by scientists at Argonne National Laboratory. A tiny particle, 1/5 of a gram, of Thulium-170 was made by bombarding Thulium-169 with neutrons in a heavy water nuclear reactor in Idaho. The radioactive thulium provided the X-rays without a power source, making this a very portable X-ray unit weighing less than 50 pounds. You won't be seeing these in your doctor's office, but they do have some specialized industrial applications. It's also been proposed to use much larger quantities of Thulium-170 to power autonomous underwater vehicles, or AUVs, with a device called an MMRTG, or Multi-Mission Radioisotope Thermoelectric Generator. These have already been used on space missions. Essentially, there's enough radioactive material to become hot, and this heat is turned into electricity. This is the MMRTG used on the Curiosity and Perseverance Mars rovers, mounted on the rear of both, but these use plutonium, not thulium. Adding thulium compounds to ceramic glazes can give fluorescent blue colors. Under normal room light, these colors are invisible. Under ultraviolet light, they glow. Here you see 3 different rare earth colors. The red is from samarium and europium, the green from terbium, and the blue from thulium. A bit of thulium or thulium oxide mixed into glass will tint it a yellowish color. Rare earth elements introduced as impurities called dopants into yttrium aluminum garnet or YAG laser rods can cause the output laser light to occur at different wavelengths. The most common ones are neodymium YAG lasers, which produce light at a wavelength of 1064 nanometers, or about 1 micron in the infrared. Holmium chromium thulium triple-doped YAG has a high efficiency. It lasers at 2080 nanometers, or about 2 microns in the infrared. Erbium-doped YAG lasers at 2,940 nanometers, or almost 3 microns. Ytterbium-doped YAG lasers at 1,030 nanometers, and neodymium-cerium double-doped YAG is similar to neodymium YAG, lasing at the same infrared wavelength as plain neodymium YAG. Lasers work by a process called stimulated emission. First, one has to bring atoms, in this case thulium atoms in the YAG crystal, into an excited state. This can be done with a flash of light. A single photon entering the crystal can stimulate an excited atom to give up its energy as a photon. These two then continue in the same direction, causing a cascade of other atoms to give up their energy. A larger, meaning brighter, light pulse exits the crystal, or, in other words, is amplified. As a matter of fact, the acronym LASER stands for light amplification by the stimulated emission of radiation. And now you know why. This is an erbium fiber laser amplifier, but thulium is used in similar devices, but for different wavelengths of infrared light. A dim pulse of light comes in on the left-hand fiber, passes through an excited thulium YAG crystal, is amplified, and exits the right-hand fiber optic, amplified brighter than the original light pulse. Thulium lasers use invisible infrared laser light blasts to break up or dust kidney and bladder stones by hitting it with trains of laser pulses. The laser light pulses travel through a fiber optic catheter, which is attached here on the laser system. This laser can also be used to treat soft tissue problems in the prostate. The thulium laser offers some advantages over the holmium laser we saw a couple episodes ago. Your body does not use thulium, but probably still contains a few micrograms or nanograms or femtograms absorbed from the environment. As usual, we'll end this talk with Mary Soonley's elemental haiku about thulium. 15,000 steps to gain the first pure sample. Extreme chemistry. In the next program in this series, we'll examine the next lanthanide element, ytterbium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element thulium.